Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 2.1, Defining the Derivative at a Point. To start our conversation, we'll look at a concept we're all very familiar by this point in time in our math careers, the concept of slope. Right now, when you hear the word slope, you might think rise over run, or you may even remember the formula for slope as m equals y2 minus y1 over x2 minus x1. And if we took a look and investigated this graphically, and we just plotted our two arbitrary points, x1, y1, and x2, y2, our computation would calculate the slope between these 2 points. Now let's change up our notation a little bit to become a little bit more function-oriented. So instead of y2 and y1, we can replace those with function notation. We can write f of x2 minus f of x1 over x2 minus x1. Same idea of slope, just a change in notation. And to correct for that, we can go over to our graph and replace the y2 and y1 over there with the new function notation. We're going to make another change in notation, change in variables. This x1 and x2, we're going to change. Instead of x1 and x2, we're going to replace it with a and x, which might seem arbitrary, but it'll help us with our notation later. But now my function notation is a little bit messed up. Instead of x1 and x2, I have to change those now to f of a and f of x. Now, with all of our tiny notational adjustments, we can rewrite the formula for slope as f of x minus f of a all over x minus a. And all I want to do is emphasize right now that this is the same formula for slope you've been using since 7th or 8th grade, just with a new shiny presentation. Now, if we go back over to our graph, and instead of thinking of this as just a line segment, let's draw an arbitrary function that connects f of a to f of x. I'll do it a little bit better here. And now we can see that this blue line, all it really represents is the slope between two arbitrary points on a function. Now, this is an important distinction. Up until now, slope for us has always meant the slope between 2 points. So this blue line here is neither the slope at x or the slope at a. It's essentially the average slope between x and a. This is where calculus and the derivative come into play. We want to find the slope at a. So what do? We move this point x closer and closer to a, and as we move it closer and closer to a, our slopes will keep subtly changing. I'll draw a couple in here. So if we moved x a little bit to the left and made a new x value and connected a to that point, we'd have a slightly different slope. If we move x a little bit further and make a new point and connect it to a, we'll have a slightly different slope. And the idea here is to move x infinitely close to a as possible, and then compute the slope as the 2 points converge on each other. Now, if we track the slopes as x converges on a, we'll see how this idea of the slope between 2 points converges to the idea of the slope at 1 point, specifically that point A. I have it drawn here with that purple line. And this far in the class, we've discussed what it means for x to get closer and closer to a. That's very specifically a limit. So we can actually write this idea down as the limit as x approaches a of the slope between x and a. So the limit as x approaches a of f of x minus f of a over x minus a. And this right here is our formula for the derivative of a function at a point. And we write f prime of a little apostrophe on our f, indicating the derivative at a. So all I want to emphasize right now is that this derivative, this f prime of a, is just a slope, but no longer is it a slope as we used to think of it, as a slope between 2 points. It's a slope at a very specific moment in time, exactly at a. In essence, when we compute a derivative at a, we are finding the slope of the tangent line to the function f of x at x equals a. Future, we're going to learn plenty of shortcuts on how to find derivatives at a point, But for now, let's use this definition of the derivative in an example. Here we have a function f of x equals x squared minus 3x plus 1, and our task is to find f prime of 2. We'll use the definition of the derivative, and to start we should just write it out to help us remember the formula. So f prime of a is equal to the limit as x approaches a of f of x minus f of a all over x minus a. So if we're going to compute f prime of 2, we will need the limit as x approaches 2 of f of x, but we already know what f of x is. That was given to us. That's x squared minus 3x plus 1 minus f of 2, which we don't know that yet, all over x minus 2. So if we write out the formula for this limit, it makes sense that the first thing that I need to find is f of 2. Easy enough. Finding f of 2, we'll plug 2 into our function. That's 2 squared minus 3 times 2 plus 1. And that should be 4 minus 6 plus 1, which would be negative 2 plus 1, so negative 1. So we can rewrite our limit substituting in the negative 1. The limit as x approaches 2 of x squared minus 3x plus 1, no need for these parentheses anymore, minus negative 1, which we can simplify and adjust really quickly to just a positive 1, all divided by x minus 2. Cleaning up this limit a little bit in the numerator, we can add the 1s. So we get the limit as x approaches 2 of x squared minus 3x plus 2 all over x minus 2. And we can try to evaluate this limit by plugging in 2, but I'll leave that up to you to confirm. Since it will be 0 over 0, I'm going to go ahead and just factor the numerator, and that would leave us with x minus 2 times x plus 1. Nope, not x plus 1, x minus 1, all divided by x minus 2. We can see that we can cancel out the x minus 2's. Simplifying our expression, we now have the limit as x approaches 2 of x minus 1. We can now plug in 2 accordingly, and 2 minus 1 will be 1, thus telling us that f prime of 2 is equal to 1. And just to translate this conclusion back into language that we're more familiar with, we just found that the slope of the function, the slope of f of x at x equals 2 is equal to 1. Now we've learned and seen how to use the definition of the derivative at a point. Check out our next video to learn the more general definition of the derivative of a function at any value of x. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.